All right, so welcome to Speakeasy JS. This week, we are going to have a really special talk from our speaker, John Hiesey. And as you can see here, this is going to be part of what he's talking about, which is what opened our meetup for us today. So real quick, before we go any further, just want to welcome our other panelist who's joining us this week, Makola. How's it going, Makola?
Hello.
Amazing. And now I'll introduce our speaker. So this is John. And John is, oh yeah, go ahead, John, say hi.
Hi. So I'm going to be explaining this 1960 color TV that I've been repairing. It's been kind of a long-term project, and I've wanted not just to make it work, but also to understand how it works and kind of like sort of not quite end to end, but from like theory to how do you actually get it looking good. So I'm going to talk about a little bit of all of this. So just for very brief context, 1960 was really early for color TV. So this would have been a very expensive TV in its time. I don't have exact prices, but maybe like $900-ish, which would be probably like $10,000 adjusted for inflation. And in addition to having color, the other special thing about this TV is it has a remote control. So that was also very unusual. It's an ultrasonic remote. So it's actually electronic. There's one transistor in the remote control that emits sound, that ultrasound that you can't hear, that can adjust the tint, color, volume, and channel. And that was pretty special when this came out. So let's get into it. So I'm going to do most of this presentation on paper, just drawing things and then showing pictures of the TV. So can we get the paper camera? All right. So it's lagging. Oh, there we go. Okay, so a little bit of history. So people started trying to figure out how to make TV work back in the 1920s. That was the very beginning of TV, and it was all done experimentally, mechanically. There were many ideas. The most popular idea was this thing called, is the video working for you?
Yeah, it's good.
Okay, it's lagging for me. That's all right. There was this thing called a Nipkow disc. So you had a disc that spun really fast at your frame rate, so like 60 times per second, and it had little holes in it at different, in sort of a spiral pattern, and you had like a single light bulb behind it. So as this rotated, first this hole in you'd view the picture like in a little tiny rectangle like this, and one hole would go past, and then another hole would go past, and then another hole would go past as it rotates, and then it would start over. And so this was this is the first idea of how do you send a picture over a wire. So you have a picture, or over the air, you have a picture that you're trying to show that's this two-dimensional thing, and you're trying to figure out how to send it over a single signal, which is like a voltage or essentially the intensity of the radio waves that's like faint and then strong and so forth. So how do you do that? So the answer is you scan. So you go left to right and then back like a typewriter, and left to right and so forth. So the mechanical approach was the first ideas. You have this thing spin, and then you just have a light bulb behind it that varies in brightness. So if you want like a circle, if you want like a black circle here and the rest of your screen is white, what you'd do is you'd have the light on here, on here, on here, on here, and then off, and then on, and then on and off and on, and so forth. And you could do shades of gray that way by turning the light on and off. Problem is these disks didn't work very well. You had as many lines, like scan lines. Here they're going horizontal. Here I'm showing them vertically. You had as many scan lines as you have holes in the disk, so they got absolutely enormous. That didn't work very well. So also in the late 20s, there was finally this guy, Philo Farnsworth, developed all electronic TV, so no moving parts to display a TV picture. And you might ask, well, how does that work? Like, that's basically the TVs that we all kind of, well, the older of us grew up with, and the younger of us may not really remember, but CRT TVs are essentially what he developed, not only the TV set, but also the cameras to go with them. So I want to explain a little bit about how those work, just in general. So before you can understand how a CRT TV works, you have to understand a little bit about vacuum tubes. So a vacuum tube is what we had before transistors, and they can do a bunch of different things, but they all start kind of like a light bulb. So you have a glass bulb like this with a vacuum inside, and you start with, you have a filament. I'm just showing this as like a piece of wire. So you provide, there's like a battery that powers it. Just all this is doing is making this hot. So this is going to be glowing like orange hot, something like that. And what that does is it makes the electrons that are floating around in the metal, everything has electrons in it, but the electrons will be willing to leave the metal and kind of float around in what's called a space charge. So these electrons will just be kind of floating around in the vacuum near the filament. And then what you do is you add a metal plate on the other, over here, some distance away, can be pretty close. And what happens is if you make this more electrically positive charge compared to the filament. Now this, you'll notice I drew a battery here. So there's a little bit of voltage across this to power it. But let's say there's 6 volts to power the filament. And then suppose we apply, I don't know, 100 volts between the filament and the plate. This means there's an electric field in here. So the electrons are negatively charged. So they get attracted to the positively charged plate. So these electrons will flow this way towards the plate, and they'll go, through the circuit, whatever is providing the power to our circuit. So, but what's interesting about this is that if you change the polarity and you make this negative and this side positive, then the electrons here will be repelled by the negative charge over here, so nothing will flow. So this is a simple, basically like one-way valve for electricity. Electrons can flow from the hot side, which is the filament, to the cold side, which is the plate, but not the other way around. So that's the most basic type of vacuum tube. And this was actually discovered by Thomas Edison. He called it the Edison effect, but he didn't really find anything useful to do with it. That didn't come till quite a bit later. So the next invention, the next idea in this is you can put a little screen of wires in here called a grid. And now you can use, there's sort of 2 different electric fields. There's the electric field between the filament and the grid, and there's an electric field between the grid and the plate. And both of these electric fields have to pull the electrons this way for them to flow. And what that means is you can make an amplifier with it. The amount of current that flows through here is that goes from the filament to the plate depends on largely on this electric field on this side. So by changing this relatively small amount of voltage on here, you can control a much larger current. So that's why we say it's an amplifier. It's a small amount of voltage and current on here can control this. It's like a valve for electricity that you can control with electricity. So it's like a valve, and they're called vacuum tubes. Are called valves in at least the UK and many other countries. So how do you make? Okay, so what does this have to do with TV? So the first thing this has to do with TV is my TV, like pretty much all electronics from this era, didn't have any transistors in it, except for the one single transistor in the remote control. It used entirely these vacuum tubes to do all the work. So here's a selection of vacuum tubes from the TV. This is a diode, which means it's just got a filament. You can't really see inside here because there's not enough light, but you'll see these two wires in the middle. Those are powering those are the filament wires, and then the plate is the cylinder on the outside. So this device, the filament is heated up by power put in on the base side over here, and then electrons can flow from the base side up to this cap on the top, which is the other connection. So that's sort of the most basic type of vacuum tube. And then we have lots more fancy ones that let you amplify and control things. This one basically has two vacuum tubes in the one single glass blob, glass envelope. But it's basically exactly like I drew. There's a filament and a grid and a plate. But what's really interesting is you can actually make a TV screen out of these. The actual cathode ray tube that you're used to seeing is just a vacuum tube. It's just the filament is way in the back, and the electrons are shooting out towards the screen. And the filament and the electrons hit phosphors that glow on the screen, and that's what makes the light. So to look at this from the side, we have a neck, and then we have a bell. So this is what a TV tube, picture tube looks like. So this is the screen that you look at, and there's a filament back here that makes electrons come off of it. And then there's a grid of wires that can control the flow of electrons. And then there's actually a few like rings of metal that serve like the plates, and the electrons actually get pulled through these and focused into a beam. So these electrons shoot through here, and if this is all we had, they just make a bright dot in the middle of the screen, which isn't very useful. So what we do, so this would make a light. And in fact, there were like jumbotrons made in the Soviet Union in like the 80s that basically used one of these entire things as a single pixel. But you can make it display an entire picture by bending the beam so that it can aim up and down and left and right and scan across the screen, like we were talking about, by having electromagnets that supply magnetic fields going in 2 dimensions. So what we have to do is, so the way a TV works is it's got this electron gun in the back and these deflection coils. So that's actually how a TV screen itself works. And that makes a black and white picture. And how do you make color? I think that might be the next the next question. The way you do that is a little bit clever. There were actually a few false starts on this, but what eventually got come up with is you have 3 of these electron guns. And on my TV, they're arranged in a triangle, like this, kind of. But I'm going to draw them in a line, which is actually how many later TVs worked. So you have these 3 electron guns that shoot out 3 separate electron beams. And you have this thing called a shadow mask that has little holes in it. And then what you do is there's the phosphors can be made in different colors. The phosphors are just the things that get hit by the electron beams and light up. So they're the things that actually convert the electrons into light you can see. So what you do is you make it so, let's call this red and green and blue. You make it so that the red beam, when it goes through this hole, it hits a red phosphor here, and when the green beam goes through the same hole, it hits a green phosphor. When the blue goes through the same hole, it makes blue. And then the same thing for the second hole. So red, if you aim this through, there's a red dot of phosphor that emits red light here, phosphor that emits green light here, and phosphor that emits blue light here. So that's why there's like that pattern on the screen. So that's conceptually how the screen itself actually works. So then the TV's job essentially is to take in an electrical radio signal that's just essentially
Video
stronger
just
and
cut
weaker
out.
radio waves, and convert that's your input, and it converts it into the voltages it needs to change the brightness of the red, green, and blue, and to point the beam around on the screen to the right place. So it has to scan left and right, and it has to scan up and down, and adjust all these brightnesses. So that's kind of the big picture of how the TV works. So now I'm going to show you a little bit show you a diagram of how this particular TV works. I should have a better copy here. So this is a schematic diagram. Probably looks a little bit intimidating, but the basic idea is that you have your antenna over here, and this is the tuner that selects a particular channel. So it gets amplified a bit, and then I won't go into how the tuner exactly works, but roughly speaking, we have TV channels. This TV is so old it only picks up VHF TV, VHF, which means it gets channels 2 through 14. And each of those channels has a particular frequency range, just like Wi-Fi channels, except unlike Wi-Fi channels, they don't overlap. So like channel 2 is between like something like 65 and 71 megahertz. I don't think those numbers are right, but each one is about 6 megahertz wide, and this is to like 77. So the tuner selects a particular channel, and then it goes over here to the IF circuit, which amplifies and filters that more precisely to get out interference from neighboring channels. And then what we end up with is the video signal, which is just instructions to the TV. This is after this part. These wires here are like what you get out of your yellow cable in your analog RCA connectors with the when you have the red, green, and blue. I mean red, red, white, and yellow connectors. So this is basically your yellow connector. Is the signal that comes out of here. So this part here is I'll use a different color. This part here is like the radio part of it. That's getting the doing the tuning and selecting the channel. This gives you your yellow signal. Then this part up here is the radio, is the sound. It's basically just like an FM radio. So this gives you actually this signal here it's mono, so there's only one. This is like your white audio signal is here. This is the volume control. So this part is basically the radio part, and then the rest of it actually shows the picture. And the way that, roughly speaking, works is this part amplifies the brightness part of the signal, and then this part over here deals with the color. This part here makes the electron beam go top to bottom. So this does the vertical part of the scan, and then this part here essentially does the horizontal bit. So that's kind of how the different parts work. And then this down here is a power supply, because these electrons aren't very susceptible to movement, so you need a lot of voltage. This takes about 24,000 volts, 24 kilovolts, just to power to get these electrons going fast enough to make the screen bright. So this generates 24,000 volts in using what's called a flyback circuit, which is interestingly it was really invented for TV, but it's the same circuit that's now used in like cell phone and laptop chargers to convert the high voltage to low voltage. Except in the TV, it was converting relatively lower voltage to higher voltage. So one thing about vacuum tubes is they have to run at much higher voltage than transistors. So this TV, everything runs on between 250 and 400 volts, which is a bit dangerous. So that's one thing you have to watch out with when working on these things. You should know a bit about what you're doing before you work on one. 250 volts is already more than what you get coming out of the wall outlet. 400 volts is even worse. Then it even generates 5,000 volts and 24,000 volts for various things. So that's all pretty intense. Uh-oh, are we not getting sound? Okay. So that's roughly speaking how it works. So let's actually look a little bit at these signals. For us, can we switch to my laptop? And can you switch to the color here on the projector?
Oh, yeah.
So, perfect. So what we're looking at here is some of the signals involved in the TV. So this top signal, this is actually the radio signal that the TV is getting as an input. So you're seeing that it gets stronger and weaker in amplitude. And what that means is the way it's designed, a black picture is actually full brightness, and a white picture. Uh-oh. Uh-oh.
Well, we're coming back. We're just having some technical difficulties right now.
Okay.
Do you want to keep going, John?
Yeah.
Okay.
Could you change the saturation to be 0?
Sure. How do I do that?
Drag it to the left of the rectangle. Rectangle. There you go. And maybe in the middle.
Here?
There we go.
Okay.
Yeah. Okay. So what we're looking at here is this top, the magenta is showing, this is just a graph of the antenna signal versus time. So if I zoom way out in horizontal time, each one of these big sort of blocks is the width, is rather the height of the picture. So this, from here to here, is an entire picture field, actually. So this is one picture. And if I zoom in a little bit, what we're looking at here, each one of these blocks is a line. So this is going from the left side of the screen over to the right side of the screen. So, and then, so this is left to right, and then back, and then it resets back to the left again, and then left to right again. And this is showing the radio intensity of the signal, or rather, that's actually the signal itself, more or less as it is on the antenna. And the signal on the bottom is showing the video signal. So what this means is down here, this is black, where my cursor is. Up here is white, so this is pure black. This is pure white. Down here, these are what are called the sync pulses, which are just there to help the TV synchronize, to keep the left and right and top to bottom scanning synchronized. And then so what we're actually looking at is this is essentially one slice across the picture. Can we also show the TV screen? Okay, so if you look at the TV screen, this is a slice across the middle of the screen. And
I wouldn't show that view. It's confusing people.
okay, sure. So is there a way? Okay, this is a slice across the middle of the screen. So what you're seeing here is this is the white part on the side of the screen. On the left side, this is the gray box. This is the colored rectangle. And then we're all the way to the right of the screen again. And oh, yes. So yeah, so this is it. We're looking at this slice here. So this gray section is, there's the white section, which you can't even see. It's kind of off the side of the screen. Is rather interesting. So if we zoom in a little bit more, you'll see there's this this interesting signal over here. And what this is just a little bit of a sine wave. And this is a reference signal that tells the TV this signal here basically means red. And the way the TV represents color is that this signal gets added into the brightness signal, and it's designed very cleverly so you don't really notice it. This was very much a backwards compatibility hack that was done in the 50s for how do we add color to a black and white TV signal in a way that's backwards compatible. So what they did is they said, we'll add this extra color signal in, that's this wave, and know if this wave is missing, like it is here, that means that it's a black and white picture. And if the picture contains a very slight version of this signal, like you can see here, like you can see on, sorry, let me zoom over. This is a little bit awkward. If the signal is very weak, that means that the color is very weak. And if the signal is very strong, like it is here over on the right side of the picture, that means the color is very strong. So you can also see that on the TV screen itself. The color goes from very weak to much stronger over here. And then what actually represents what color it is. That just tells you how strong the color is, not what color it is. The way you determine what the color is by the phase of it. So for us, could you turn up the saturation a bunch? Just all the way to the top right corner is probably good. Okay, so now we're seeing this really strong signal. And so we're seeing this really strong signal. And oops, what actually represents what color it is how this is shifted in time. So you can actually see this a little bit. This marker I'm moving here, the vertical dotted line, this is just a reference to help you see where things are. So I have this lined up to match this one peak here. If you can see that. So it's kind of matching this peak. Now for us, if you change the color, the hue slider on the bottom, you'll see that this whole signal shifts to the left and the right. It's a little hard to see because it's also changing the brightness, but that's a little bit hard to see. But that's the concept, is that this wave gets shifted left and right, and that indicates your color. And that's actually what the tint control does on your TV. If you've used an old CRT TV, it's shifting the signal left and right as well. So that's enough about the theory of how the TV works. Let me show you a little bit about this TV, how it works, and what was involved in fixing it. So let me go back to this camera.
Hey, I want to pause here just for a second and see if there's any questions. Mikola.
Yeah,
that was a lot.
I also unfortunately missed a little bit of this because the stream kept cutting out. So we're looking at this is an NTSC signal, right, from the TV that we're looking at there. So I don't know if we did this, but did you see the break? Oh, there's some reverb now. Okay.
Yeah, I need to. How do you?
Is it my end that's doing that? Or?
No, it's here.
Okay. So can we look at the different parts for the sort of the front porch, the sync pulse, and the color burst? I don't know. Maybe I can't hear any audio right now. But I mean, at least the reverb stopped. Yeah, I can hear.
We're having an issue with the iPhone, not letting you mute. If you try to lower the volume on the iPhone, it doesn't ever go to 0 when you're in a WebRTC call. So anyway,
that's so they can spy on you, I'm sure, right?
I think it's just so that you know that you're in a call. So anyway, John's just rigging up Sprinted 2's bedroom to get tape to put over the speaker.
Sure. I'm wondering if we can look at the anatomy of one of these H-blank signals maybe a little more closely, right? Because I want to dissect and see if I can recognize some of the pieces of it.
All right, let's put it back on the
So can we look at a full H-blank? Because I know, from what I recall, right, and we talked about this, I think, when Substack was here with the VHS stuff, right? And it's the same basic data, right? On a VHS tape, they'd have this signal, and in the radio, they'd have one of these signals. So if I remember correctly, there's like a front porch, there's a sync pulse, and there's a
Yep.
color burst and a back porch or whatever, right?
Yeah.
So did we go through the different features of this?
I didn't really. I glossed over a lot of that.
Okay.
But I can show you where they are. So this is a whole line.
Okay.
So this is the blanking pulse here.
Mm-hmm.
This is the back porch with the color burst on it here. And then this is the actual active part of the line. So this is the left side going over to the right side. This is the front porch, and here's the next sync pulse. So that's what it actually looks like.
I see. And so with the color burst, that's actually how you get the phases for the chrominance or whatever. Or I forget, that's the right term, right?
Yes, it is.
Yeah. So you basically take that little sync pulse and then you mathematically it's like a dot product, right? With the waveform to get the phases out, right?
Yes, it is.
Yeah. Okay.
If the circuit that actually does that, I can show a little bit about how that circuit works. If we go back to the paper camera. Okay, yeah. So this is the color circuit, and what's actually going on here is this is your sine wave reference, comes out here, and it generates the two color signals. This is in phase, and this is 90 degrees phase shifted, and these get combined, multiplied by the actual raw color signal coming across the line. So these vacuum tubes are essentially doing those multiplications, and then there's a whole matrix operation we do to generate the output. That's the circuit here.
Yeah. What I wonder is when they're computing the phases by doing that, that dot product, or there's probably an electrical engineering word for that, right? That I don't know. But when they're doing that, how wide is the window for the dot product that they're taking? Because they just have one wave and they're trying to measure one frequency, but the actual sine wave itself is infinite in time, right? So but when you do this dot product, it has to have maybe some decay or whatever. And so what is the actual fall off or whatever for that wave when they're doing that dot product?
Well, the frequency that it's really a frequency response. It's determined by a filter, and that filter is actually largely determined by this resistor and this capacitor.
I see.
So it's just a very simple filter, and the frequency response is around 600 kilohertz, something like that. So not very high. Right.
But it has to have sort of a finite support, right? I mean, if they don't do that, then it'll mess up, right? Because you wouldn't be able to do it.
I mean, this is all done in sort of the analog world, so you have to think about it rather differently. It's all this continuous time thing. What's actually going on is you have these two signals, and depending, it's behaving non-linearly on purpose, which is sort of the multiplication aspect of it, and then it just gets filtered by this output filter network. There's actually more to this. This whole filter network determines.
Yeah, I mean, you can think of it as kind of like an accumulator that just decays, right? It's you're basically keeping a running average or whatever of the dot product of the sine wave with the other signal, and then it, there's a feedback, right?
Yeah, exactly.
Okay.
So when there's a strong signal, it discharges this capacitor. And then when there's no signal, it gradually charges back up. You can look at it that way. So yeah, that's how this all works. And let me show you a little bit about the repair process. So when I got the TV, it was working kind of okay. The remote didn't work at all. The first thing I had to do was get some repair manual. So this is an original official, well, I downloaded this from the internet, but this is a copy of RCA's official repair manual that they would give to their dealers. And it's actually very in-depth. It describes all of these setup processes, like how to hook up all of your equipment.
Did they actually ship these with the TVs? Like, if you bought one, did you get like this sort of like tome of electrical engineering knowledge?
No, this was only for the dealers. And you also, as a consumer, you weren't expected to even be able to install it yourself. Just putting it in your living room, these were sensitive enough to Earth's magnetic field that you had to adjust. If you recall, I was drawing these diagrams of the electron beams hitting the right colored phosphors. And unfortunately, this is all subject to Earth's magnetic field and magnetic field of other equipment in the area. So there's actually magnets in the TV that you have to adjust to correct for that, even if you move it around the room, like to a different orientation.
At the end, could we actually move that TV and see what happens?
It's very heavy, but yes.
Okay, or maybe, like, I don't know, is there a way we can illustrate that effect?
Actually, yes, I have a degaussing coil.
Okay.
I can demonstrate it that way. So one of the things I had to do when repairing this TV is all of these things are sensitive to frequency. There's a bunch of filters that are designed to like select one channel and reject all the other channels, and all of these are adjustable. So the manual gives you instructions for how to test that. Essentially, what you do, in a very high-level sense, is you give it a bunch of different signals that change of frequency that changes over time, and then you measure how much signal comes out. So you have like repeating like 60 times a second. You sweep in frequency from low frequency to high frequency, and you measure the output. And the manual gives you all these diagrams of what it's supposed to look like, and there's adjustments you make. And some of these adjustments are very finicky. Some of them are literally bending wires into different shapes to change the behavior of the circuit. That part was one of the most frustrating. So yeah, that's inside the tuner. And then they have similar adjustments for, these are more filters further down in the circuit. And again, there's diagrams of what it's supposed to look like with fairly precise specifications of how strong the signal is supposed to be with each. So each of these has a whole bunch of steps of hook it up like this, hook your signal generators up like this, and then, which knobs to turn, basically, for each adjustment.
So for each of these calibrations, it's like, do this until the following condition is met and so on. And there's like a sort of flow chart for it, or do you have to like adjust multiple parameters at the same time? Because that could take a while, right?
It's a bit of a mix. Some of them are sequential, and some of them are like the instructions have a loop where it says adjust this, then adjust this, and then go back and make sure the first thing is right still.
So it's like you're doing like some kind of stochastic gradient descent or whatever.
Kind of,
like
yeah.
This terrible parameter space for this thing.
Exactly.
It's horrible.
And
what you should do, okay, here's the next version, is you should use artificial intelligence and deep learning to automatically tune your TV.
I've thought about that. That would be a fun idea. Yeah. Okay. Last thing I really want to show are just some pictures of the process. Let me switch back to the computer. Okay. So this is what the picture looked like sent to me by the previous owner of the TV, who was an antique TV dealer. He sold it to me as unrestored. So this is what it looked like. These are some ads for what the TV how it would have been advertised in the 60s. I'll mostly gloss over those. because we're running low on time.
These are pretty hilarious, though, I have to say. Some of these. What's your favorite ad? Can you maybe show that one?
I mean, I liked how this one shows the guts of the TV. So this is the picture tube, the screen, and this is the chassis, the main inside bits. And it shows some of the TV shows that we're on. I think The Price is Right is still on. Bonanza is maybe something you would have heard of. It's a famous Western. Most of these others you won't have heard of. You'll notice how many of these are corporate sponsored, though. Ford show, Chevy show, Ford. Plymouth was another auto
Harry
company.
Como's Craft Music Hall.
Yeah, Craft Company. So that was what you could get on color TV. So this is some stuff from inside. So this TV is largely predates circuit boards. So a lot of it's point-to-point wiring, which is literally what you'd imagine. It's wires going everywhere. These are some neon lights that actually aren't used as indicators, but as part of the circuit. You'll notice there's a broken wire here. I had to replace those. This is what it looks like taken apart. This is very early on. So this whole thing is sort of like a giant circuit board, but a lot of this is point-to-point wiring, except there are some actual circuit boards mixed in here. This TV at this point in 1960, RCA was gradually transitioning their TVs from point-to-point wiring, which was a lot of manual labor to assemble, to circuit boards, which were a lot more automated. So here's some of the biggest and smallest vacuum tubes in the TV. This tiny little thing is RCA's last attempt to kind of try to compete with the transistor. It didn't work very well. This is a broken solder joint. There were a bunch of these where just due to mechanical flexing, solder cracked. That still happens in modern electronics, but it was particularly bad here. This is inside the remote control. This is the transistor. It's hard to tell, but one of the wires is broken off of it here. More point-to-point wiring. This is what it looks like on the other side. So these are the vacuum tubes. Like this up here is the intermediate frequency, like the filter and amplifier for the radio signals. This is the sound circuit. The color circuits are down here. This is the brightness circuits. This is what it looks like lit up with the vacuum tubes glowing. You can see the filaments nice and bright. This is the high voltage, the 24,000 volt section. If you stick something sharp in there, it will make a loud fizzing sound from the voltage almost jumping the gap. Replacing capacitors, you can see this is an old capacitor. These are the modern equivalents, which are much smaller. Technology's come a long way. Some of the gears broke in the remote. So the way the remote works is you press, I'll show a video of it in a second, but you press buttons on the remote and it runs a motor that actually physically turns the knobs. And some of those gears cracked, so I had to 3D print replacements. This is what it looks like inside without the picture tube. This is what it looks like if you move the TV or completely misadjust the color so that the colors are all wonky.
That's an anachronism, though. You have like YouTube showing up on.
Yeah.
It's hilarious.
Broken gears again. More point-to-point wiring. This was me testing. I replaced the picture tube with a spare I had. This was how I didn't have the equipment to test it easily, so I made my own test equipment to measure how good of condition the picture tube was in. This is what the picture tube looks like. This is the electron guns. The filaments are back here, so the electrons go this way. These big coils provide the magnetic field that make it scan up and down and left and right. And this stuff is for fine-tuning the color. adjustments. More point-to-point wiring. This is the crystal that maintains that color burst frequency reference across the line. So this is the most stable frequency reference in here to make sure the colors don't shift as it goes left and right. These are the 3D printed gears that I modeled and had printed by Shapeways to replace the cracked ones. This is the adjustment process this is like following the procedure in the manual to adjust the frequency response. So they tell you like what the test jigs are supposed to look like to hook this up. This is more what the process looks like. So this device is generating a signal, and then this is showing how the TV is responding. So this is what I'm trying to make match the diagrams in the manual by adjusting the adjustments that are through these little holes in here. You stick plastic screwdrivers in here to make the adjustments. And this demonstrates this is the remote. So here I'm pressing buttons on the remote, so it's changing the channel. Here it's changing the color saturation. You call that saturation now. Here I'm adjusting the tint, and it didn't quite work. What happens is there's one motor that goes in both directions, and then these are magnetic clutches that engage one of the different knobs. You can see the knobs actually turning. And here I'm turning it off. So more frequency response adjustments. This is what it looks like underneath. It's like a rat's nest. And 3D printed gears. This is inside the remote control. Also full of adjustments. These are adjustments as well. So lots of adjustments, lots of fixing broken stuff, but it all is working pretty well now. So I'm really happy. Let's go back to butter churn on the TV for the last quick demo. Okay, cool. Sound. Okay, so here I am with the remote. I can turn the volume down. I don't know if you can see it, but this knob is actually turning as I change the volume with the remote. And I can change the color, saturation, so that's black and white. And you can go totally psychedelic, oversaturated. That's way too much. Let's go back to something normal. And you can change the tint, which you wouldn't really notice with this, but brightness. So that's like adjusting the magnitude of the signal, the amplitude of the brightness signal, or rather, no, this is adjusting the 0 point, the black point, and you can adjust. You have adjustments for synchronizing the horizontal. So this is synchronizing the left to right scan. So this is what looks like if you misadjust it. And vertical. So it has to synchronize with the synchronization pulses, and if it's misadjusted, it will roll like that. And contrast. So that's pretty much all the controls the user would see. And yeah, it sounds, I had a lot of trouble getting the sound to sound good, but now that the sound is working, I'm pretty happy with the whole thing. So that's the TV. I don't know. Is there anything else I should say? I think we're over time quite a bit. I haven't changed. I get lots of snow, but I only have an input on channel 5. Oops, I skipped channel 5. You can see the channel indicator up here.
That's so good.
2. I went past 5 again. It's a little finicky. There we go. And I have a whole setup to generate the signals for the TV. That was an interesting experience in itself. Let me just take this off. So oops, this cable is not reaching. So this is, I have my signal going through this box, which fixes the 16 by 9 versus 4 by 3 aspect ratio being wrong. And then that gets converted from HDMI to analog over here. And then this goes through a modulator down here, which lets me output it on any channel that I want. You can actually dial any frequency that you want. So 77.25 megahertz is channel 5 in this case. And here's the actual oscilloscope. So one of the interesting challenges was getting the aspect ratio right. Almost every HDMI device assumes that it's being shown on a 16 by 9 widescreen monitor. And because this is not widescreen, I got this professional video scaler, which I can control by scripts on the laptop this is connected to control whether I letterbox it or fill the whole screen and cut off the sides. I could not find a cheap consumer device that converted HDMI to analog that didn't squash the picture on most input devices. But questions? Sounds good. Let me put this back.
All right, so I'm going to read a couple questions that were way over time. I just want to quickly say that was mind-blowing, and I wish I had actually done the intro that I planned to prepare people for this talk, but you kind of jumped right into it. So if people came here expecting JavaScript, they were shown a talk that was like many levels lower than that, and hopefully. But it's totally in the spirit of our mad science theme, and like I can't believe how much time you put into this like project. How long have you been working on it for again? Since you bought the TV until today?
Well, I got the.
Oh, 1 second. Sorry, you're on mute. There we go.
I got the TV just over 3 years ago, and it's been sort of a weekends and occasional nights project since then. I would say it's probably like if I'd done it all like full time, it probably would have been like 2 months of full time work. But most of that was learning stuff. I have lots of books on TV repair, and let's see, I've got a whole collection of books and materials that I've collected while working on this. Next question.
Yeah, so we have someone asking, can you make it run a PS4?
Sure. Anything with HDMI will work.
I wonder if instead of using the tuner thing, like this thing, it takes an NTSC signal. So if you could find like an old TV tuner card, you could just like make your own, video rescaler or whatever, and then just use the TV tuner card for an output. And even if you couldn't get it to work in a new computer, you could always just run it through the network through like an old PC or something.
Sorry, I didn't quite catch that.
Like,
I think it was
instead of the rescaler, you could just use like an old TV tuner card or something for outputting this, right? Or is there a problem with that? I didn't quite get what the issue was.
Well, the rescaler is purely HDMI input to HDMI output. The reason I have it is if I just try to pass the signal through, it will display the entire widescreen picture on the 16 by 9 is the widescreen aspect ratio. It'll display that on a 4 by 3 screen. So it will be horizontally squashed. So like a circle will appear as a vertical oval. So I actually have two. I have, if we point at the TV screen, which I think it is, I actually have some scripts that change the mode of the scaler, and you can actually see more what it's doing. So I'm going to exit full screen on this and demonstrate. So this is the fill mode. So it's cutting off the left and the right hand side of the picture. The other option is letterbox. So you can see that it's not cutting the left and the right side off, but now there's black bars on the top and bottom. So it's purely a matter of, there aren't any analog. If you want to go from HDMI to analog, the signal is probably going to be wrong, because most modern devices aren't even willing to generate non-widescreen outputs over HDMI. Yeah, if you use an old video card that can generate analog video directly, you wouldn't have that problem.
Yeah. I mean, it's just, my thinking is just, I would immediately try doing everything in software, because I, am not so handy with electronics. But
so funny you say that. I did actually, and I decided not to demo that, but I have here a software-defined radio, which I'll hold up in front of the TV. And this actually can generate the full signal. Just plug this into USB and plug this into the antenna jack on the TV, and you can basically do the whole thing in software.
Cool.
It's very CPU intensive. So.
Just do it on the GPU or something. It'd be fine.
Cool. Okay. Well, do we want to do one last question? We're like a little bit over time, so I think, Mikola, if you have anything to ask, there's a lot.
I mean, you could actually, like, with that software-defined radio, you could hook up Substack's presentation into that radio, and then you could use that WebGL demo to like output stuff. Because James just did that last time, right? He actually made a thing that runs in your browser and generates an NTSC signal, and it can even render the NTSC signal.
Right. Yeah, you totally could.
Oh.
Yeah.
Yeah. Wow. So. I think we should go to the next part of the event. I wish we could keep going, but we've kind of already pushed our luck a little bit. We're like, like way over time. But anyway, John, thanks so much for the talk. Do you have any last things you want to say, or Mikola, any last words to our viewers?
I think it's really cool. I like it. I think that TV looks awesome. I want one in my living room.
It's huge.
Yeah, I feel
it weighs about. Well, here's, if you can put it on this camera. You can see how big it is. So that's the front, and then this is how big it is. This is a CED player. That's a topic for another time. There are movies on vinyl records.
How did you find one of those? That's so weird.
The CEDs?
Yeah, I thought that thing died. Like, I didn't know they actually made those.
My grandma had some from the 80s. So this is
inside grandma.
It's a little dark.
Yeah, but you can see the tubes are lit up. They're nice and bright. So I think that's about it.
Cool. I really appreciate you sharing all that, John. I think that this talk was basically like you going into like a cave and finding like an ancient tome of like forgotten knowledge, and then bringing it back and preserving it for future generations. I feel like there's lost knowledge that you've like just rediscovered here for us. I don't know how many people know this stuff anymore. Like, seems like I don't know, probably not that many.
Most people who know this stuff were old TV repair people, and they're usually either not in business or not alive at this point.
Right. Cool. Well,
definitely a lost art.
Yeah, definitely a lost art for sure. Cool. Again, I appreciate it. So let's go now to the last bit here. So next week we're not going to have a speaker because it's Christmas. So enjoy Christmas. That's the 25th. We're going to skip that, and then even the week after that is actually New Year's on Friday as well. So the next 2 Fridays are there's no Speakeasy JS, but we'll be back in the new year on January 8th, I think, with more stuff. And we already have talks planned all the way until February. So yeah, that's really exciting. Got a great lineup of talks coming up in the new year.